Our next talk is model-based testing and analysis of the cyber resiliency of cyber physical systems by Dr. Roshan Thomas. Roshan is a principal InfoSec scientist at the MITRE Corporation, where he leads cybersecurity research and innovations related to model-based security engineering, as well as assurance and trust management in cyber physical systems and autonomous computing. Roshan, take it away.
Okay, good afternoon. So I'm going to be talking about the SCAPS project, and the SCAPS stands for Secure Control Architectures for Cyber Physical Systems. So MITRE is doing a lot of research, has been doing a lot of research over the last few years on digital engineering and model-based engineering and model-based design, and how to incorporate security analysis into the model-based design process. Okay, so the work that I'm presenting is part of a pattern that MITRE has. All right, so the domain for this research and for this SCAPS project is really cyber physical systems. So as you all know, you can abstractly think of a CPS system as something that has controllers, sensors, actuators, and these are all involved in controlling the physical operations of a system. And then you also have an operator or a number of operators interacting with the system. So there are very diverse sectors for this, everything from industrial control to aviation to automotive to the electric grid to weapon systems to medical. So that's the domain that we are dealing with. So from a research standpoint, the critical question that we are asking and the problem that we are trying to solve is that of how to systematically assess design vulnerabilities in cyber physical systems. And how do you increase the efficiency and accuracy of security analysis? So this is scientifically very, very challenging. The first challenge there is how do you go about systematically and efficiently enumerating the attack space and the attack surface for any given cyber physical system design? And how do you analyze where safety-oriented and fault-tolerant designs are inadequate to withstand cyber attacks? Because traditional safety mechanisms are designed to deal with independent benign failures and not necessarily coordinated and malicious failures. And then the research challenge again is how do you systematically analyze and measure the risk? And then how do you eventually converge on an optimal design where you can mitigate those risks? So SCAPS is, again, it's part of model-based security and simulation analysis technology. And there was an NDIA report in 2011 that really called for the accelerated adoption of model-based engineering. So that's what's motivating us. So everybody here is familiar with model-based engineering. So what we are trying to do is do research so that we can incorporate security engineering into the model-based engineering approach, to the model-based engineering paradigm. So we have AADL, we have SysML, all of these things are great paradigms for model-based engineering. But how do you incorporate security analysis into it? We want to be able to capture security dependencies between diverse system aspects. We want to understand the dependencies between security and safety. We want to be able to measure resiliency in relation to security attacks. And we want to be able to enable model in the loop and simulation in the loop testing and eventually converge on a security optimized design. So our approach in SCAPS is to basically take the models for a target system. So you have the AADL model. You may have other lower level models like simulation models like Simulink. Take those models and inject effects into them systematically, and then ask the question, and then observe what effects you are seeing on the physical system. And if we are seeing bad effects, if we are seeing that the security effects that you are injecting are in some way impairing the physical operation of a system, then you want to do some kind of analysis and then converge on an optimal design. So this is the whole approach behind the SCAPS project, the SCAPS research. Okay, so drilling down a little bit more into the technical approach, the way we look at cyber physical systems is that there are many layers. So at the bottom, you have the actual physical system. So you have your sensors, you have your actuators, you have your controllers. And above that, there is a control element, and that's basically your control algorithms. And above that, you have a cyber layer. And the cyber layer is really how the control algorithms are computerized and rendered in a computer-based system. And above that, you have the user and the mission layer. So the focus on SCAPS type of analysis is really in the interface between the cyber and the control. We ask the question, the computerized rendering of the control algorithms and the control system, if that was perturbed through cyber attacks, we want to know what is the effect on the control system, and then what is the effect on the physical operation of the system. So this is really what we are trying to do. Okay, and the way we do is we break open the interface between the cyber and control layer, and we incorporate attack effects into the AADL model and map them to simulation models. And then basically these attack effects are injected into the simulation models, and then we study the physical impact. And this is a picture again that just goes over what I just said. So basically you have your AADL model, and then you also have your Simulink model. We inject effects at the AADL layer, and those effects are mapped to effects on the simulation models. And then we observe what happens to the physical system. Okay, so what we have done is built this SCAPS Workbench tool suite. It's a web-based system. It allows you to import the AADL and simulation models. And then you basically can import a library of effects. And then also you can integrate with the failure annex of the AADL. So you can import the fault models, the fault trees. And then basically you can, as an analyst, specify which of these failures and faults are cyber inducible. And then you select the ones that are cyber inducible. And then basically you can come up with a set of attack scenarios and a package of attack effects, and then subject the AADL model to these effects, which will then get mapped to Simulink. And then eventually these effects are introduced at the Simulink level. And then you run simulations, you run batches of simulations, and you observe what happens to the system. Okay, so there's a conceptual model behind the SCAPS approach. So you take any system, you can break it down into a number of mission essential control functions. So you take an aircraft, a control function might be to pitch the nose up. Another control function might be to turn the aircraft left. Another control function might be to pitch the nose down for landing. So to do those functions, to execute those functions, a number of control surfaces have to move, and a number of sensor readings have to govern the algorithms that basically decide how much the control surfaces should move. So you take any system, you can break it down into a number of mission essential control functions, and then you have to think about what are the hazards and accidents that could happen. Okay, and a hazard and accident, or an accident happens when a safety constraint is violated. So there are a number of safety constraints which govern the safe operation of the system. So you have to model and understand which safety constraints will be violated for a particular set of hazards. And then for these accidents or hazards to occur, there are particular faults. So an event of interest is basically a fault of interest. And faults obviously are made up of failures. Okay, and there are environmental enablers which will contribute to the hazard. Okay, so this is the way we model the system. And then we also have resiliency metric. We have something called the mission degradation loss to cost ratio. I won't talk about it too much in this briefing for the lack of time, but it really measures how much of mission critical functions are lost as a result of a specific impairment of control functions. All right, so what is the value proposition for something like this? The value proposition for a tool like SCAPS is basically to really test and understand the vulnerabilities in the system. So you can imagine there are multiple audiences for this. The first community would be system design and test engineers who at design time want to uncover flaws very early and before the system goes into production and deployment. Then there are forensic analysts who could use a system like this to do post-mortem analysis. So you have deployed the system in the field, and then you are getting field reports saying there are some things which are going wrong. And then you want to do forensic analysis. So this will be useful. There are red teams that could use the SCAPS approach to basically figure out what is the next set of attacks we need to inject in the system based on an ongoing exercise in red teaming. And then, of course, SCAPS can be used for certification. So the analogy of the UL labs. So you can imagine a third-party lab that is involved in certifying. So you have the manufacturer of a control system, you have the consumers, and this third party can come and use the SCAP system to run through a number of scenarios and certify that the system does not have any bad effects. The system does not misbehave with respect to a prescribed set of scenarios. Okay, so let me move a little bit into the illustration of how SCAPS works. So as I said before, we are dealing with cyber physical systems and we're dealing with control systems. So here is a simple example of an analgesic pain management system in a hospital. So you can imagine a patient, he's post-surgery in a lot of pain. So there's an analgesic pain management system that is managing the pain. Whenever the pain gets unbearable, the patient is allowed to press a button and more morphine or some other pain numbing drug will be injected into his body. Okay, so there's a regulatory feedback system inside the machine that does this. Why is that? Because you don't want a patient to overdose. So there is a control system here which monitors the heart rate and the oxygenation levels. So if at any time these vital signs get unstable, there's a pulse oximeter which is tracking this, the controller will take action. So if the heart rate is unstable or the oxygenation level is not sufficient, the controller will issue a stop message to the pump. So the infusion pump is the one that injects the medicine whenever the patient presses the button. So the controller will say, nope, the patient is unstable, issue a stop message to the pump saying, do not dispense any more medication. Now, if the vital signs degrade to the point where death is imminent, then basically the controller will wake up and issue a very urgent alert to the nurse's station saying, go and take physical control because the situation is very, very bad. So what the SCAPS system does is that it looks at these feedback loops. It looks at the regulatory processes within this pain management system. It identifies these pathways, the control feedback pathways, and it injects attacks. So the first attack it does, it will inject an attack to suppress the stop command from going into the pump. And next, there's an advisory alert that is sent to the nurse. It will suppress that too. Now, if the death is imminent, it will suppress the third message from getting to the nurse's station. So by suppressing these messages, the regulatory feedback loop is interrupted. And as a result, what happens is you can see here, the regular operation, everything is regulated with the regular rhythms. Okay, you can see that everything in the heart drug level goes up and down. The heart rate is going, it's kind of, oscillating in a very, very steady pattern. And as soon as the attack begins, you can see that the drug level kind of goes down. You can see the heart rate going up and the oxygenation level is going all over the place and the patient has a heart attack. And as soon as we stop the attack, everything resumes. But in the real world, the patient would have died. Okay. Similarly, we did some experiments with a fighter jet schema. And what we were able to show here is that you can interrupt the safe operation of the fighter jet. So here on the left, you have your AADL schema. And here on the right, you have the Simulink schema. The blue part of the Simulink schema deals with the control processing, and then the yellow part here is really the physical aspects. Okay, so what we are seeing on the right here is the controller module. Okay, and there is something called the pitch rate that is input into the controller. The controller has 4 inputs, as you can see here, including inputs from the pilot. But the third input here is basically the pitch rate. And what we were able to do is inject an effect which suppresses or delays the pitch rate. Okay, so here you have the effect being introduced, and here you have the controller. And what the controller will do is when it gets the pitch rate, it does a number of calculations, issues a control command, and that control command is sent to an actuator model, which does a lot of precise physical calculations and then sends the exact sends a message which tells the aircraft dynamics model exactly how much you want to move a particular surface. Okay, so we were able to basically interrupt this sensor feedback on the pitch rate, and we were able to basically make the aircraft oscillate. Okay, so what you will begin to see is that the pitch rate is beginning to go all over the place. Okay, so the state estimation algorithms are getting messed up because the pitch rate is no longer available in a very, very reliable way. And as a result, the aircraft begins to oscillate, and eventually the G forces were so high and the aircraft crashes. Okay, so this is really kind of the core innovation behind SCAPS. You take an AADL model, okay, which is an abstracted view. It's not the same thing as a Simulink model, right? Because you're abstracting the software and hardware architecture. You're looking at the essential components, essential elements, and you're injecting effects into the AADL model. And those effects are translated into effects at the Simulink level. And then the Simulink simulations are run, and then you can show the result on the physical system. So how do we do this? What we did was, from a research standpoint, we looked at all the modeling elements in AADL. So we have all these abstractions: process, thread, data, subprograms, processor, memory, bus, device. For each of these things, we asked the question, what are examples of confidentiality, integrity, and availability attacks? And we focused really on integrity and availability. We were not that interested in confidentiality, although in certain cases one could think that the configuration of a particular CPS system is very confidential. But our focus was on integrity and availability. So you can see, for example, if you took the bus, an integrity attack would be tampering with the bus contents. An availability attack would be to disrupt the transmission and the data movement on the bus. So for each of these elements, we broke down, identified a number of cyber-induced effects, which could be indicative of false. And then we boiled them down to these primitives of delay, drop, blind write, and write. And then we can convert that to basically specific effects at the control layer. So we start with the fault type on AADL components. We reduce them to a number of one of these four primitives. And from there, we map it to specific what we call control hooks. These are control system effects. So what the SCAPS system allows you to do, here's an example of the analgesic pain management. It shows that in an abstract way, the schema. It allows you to pick the cyber effects. And then, so you can see on the left here, these are examples of all the cyber hooks. It allows you to pick these things and drag and drop these effects on the pathways between these different components. Okay, and then it will allow you to run simulations. So here is an experiment. So let's say this is experiment 75, and you can choose a number of attack configurations. Each configuration is a combination of certain cyber effects. And then you have different batches. So you can create batches of simulations where each batch may have a slightly different value for an experiment parameter, okay, or for an attack parameter. And the system will run these simulations on the back end and show you the results. It is looking out for events of interest. So if you see the stall of an aircraft, or if you see the pump is not working, you specify the events of interest or faults of interest, and the system will let you know if these faults are occurring in the specific runs. So here you can see it's showing you the criticality of the events, and it's showing you what exactly the faults are. Okay, so and there are all kinds of visualizations we've built in. So here is an example of visualization where it's showing you that basically for this particular, so there are a number of configurations. Each box here is, each rectangle here is a different configuration. And it's showing you that in configuration 1, there is a very, very safety critical event, set of events that were observed. In this case, it is stall and loss of pitch control. So anything that's critical is in pink. So we have different colors depending on the criticality, and the area of the rectangle indicates the number of events or the severity of the events. And there are different views to this. We can look at it based on events. We can look at it based on the attack hooks or the effects. We can look at it based on experiment runs, experiment batches, experiment events. So a number of ways to slice and dice and view the effects of the simulation. Okay, and then basically we've also integrated fault trees. So we take the failure annex and we can generate the fault trees, and then we can allow an analyst to pick and choose the faults which are cyber inducible. And once we do that, what our system does is it begins to do what's called a cut set analysis. It begins to ask the question from the bottom all the way to the top event, the failure event. In this case, as an example, landing gear is inoperative. What are all the different pathways where the failures or faults can be cyber induced that will lead to a landing gear becoming inoperative? And based on that analysis, it begins to collect the set of effects, and then it basically injects those effects and does the simulation using the backend Simulink system. So this is the kind of the developed features. We started with a lot of automation and assistance and analytics and visualization. We moved on to fault tree and kill chain support. And we also have hardware in the loop. So you can have a particular component of your system in real hardware and then combine it with software. And then we are moving into what's called intelligent attacking and red team emulation and planning, and then security optimized design. Okay, so we are doing a lot of work on what's called intelligent attack generation, which is basically looking at a number of pieces of information and trying to figure out how can you attack the system intelligently. So it looks at the schema structure, it looks at the fault trees, it looks at likelihood and severity information, it looks at what we call safety design dependencies, it looks at a number of control functions, and then it figures out how to attack the system. Okay, so here's a great example of a particular pattern. So here you can see that the radar acquisition and image acquisition are both inputs to obstacle detection. So this is an example of what we call a fan-in pattern. You can have other examples of what we call fan-out patterns. So what the system will do is look at these kinds of patterns and figure out smart ways to attack that. Okay, so that is basically a summary of SCAPS. Now the future evolution is really to automatically craft attack scenarios based on the system models and based on attack TTPs. So some of you are probably aware, MITRE has something called the attack threat framework. We also have something called ICS attack, which has a breakdown of different tactics and techniques to attack ICS systems. So we can use those tactics and techniques and then import them and the models into a planning and runtime engine, which will basically craft automatically a number of attacks and subject the system. Okay, so that's sort of a summary of what SCAPS does. It combines AADL and Simulink models. It analyzes the system from a high level model-based standpoint, looking at the AADL elements, and then it drills down into actual simulation models, and then looks at the effects, the physical, what physical effects can be brought about on the physical system. Okay, and there's a lot of research directions that we are looking into, including intelligent attacking and how to derive automated mitigation strategies. So let me stop there and take questions.
Thank you, Roshan. We've actually almost run out of time, and I sort of have to wrap up. But I want to thank you very much. It was very interesting, and seems like a really innovative use of AADL within something that could really be useful for many different applications. So I believe our next talk begins at 2:10. So I want to thank you again, Roshan, for the talk, and we'll see you in about 5 minutes. Thank you.
Okay, thank you.